Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Imagine stepping outside tonight, assuming it's a clear night, wherever you happen to be listening to this.
Right. Hopefully no clouds.
Yeah, exactly. And you look up at the sky, you look past the streetlights, past the airplanes, and you try to spot Alpha Centauri.
Which is our nearest stellar neighbor.
Right, the closest star system to our own solar system. It just sits there in the darkness, glowing faintly, and because we call it the closest, it feels like it is just, right next door in the grand cosmic scheme of things.
It does feel that way, yeah.
But distance in space is it's a really tricky concept to wrap your mind around. Because if you were to actually try to travel there right now, using the absolute pinnacle of our current rocket propulsion technology.
The very best engines we've ever built.
Exactly.
Yeah.
You would be embarking on a journey that would take tens, if not hundreds of thousands of years.
Hundreds of thousands.
Yeah.
I mean, it is a timeline that completely defies human comprehension. Just to put that into perspective, human civilization as we know it, like recorded history, agriculture, cities, that's only about 10,000 years old.
Yeah. So 100,000 years is...
It's essentially forever. So a journey of 100,000 years means you aren't just sending a crew of astronauts. You are sending an entire civilization.
a whole society in a can.
Exactly. You would be launching a generation ship where the people who actually arrive at Alpha Centauri wouldn't even remember Earth. They would have to survive, evolve, and basically sustain themselves for countless generations in the void just to reach the closest star.
Which, frankly, makes interstellar travel seem practically impossible.
It really does.
It feels like this hard boundary drawn by the laws of physics. But today, we're going to explore how that timeline is currently being challenged in a way that honestly sounds like pure science fiction.
It really does sound like sci-fi, but it's happening right now.
Right, because what if that mind-boggling multi-millennial journey could be compressed down to roughly 20 years?
20 years. A single human generation.
Right, a single generation.
Mm-hmm.
A spacecraft launched today could actually be intercepted by the people who built it. We are talking about fundamentally escaping the limitations of traditional fuel-heavy rocketry and entering an era where we propel objects through the vacuum of space using literally nothing but light.
And that is the paradigm shift we are witnessing right now. We are basically moving away from the brute force of chemical explosions.
Which is really all a traditional rocket is, right?
Yeah, exactly. A highly controlled explosion. And we're stepping into this entirely new realm of optical propulsion and microscopic levitation. It's a shift from fire to photons.
I want to frame this properly because the timing of this shift is just incredible to watch unfold. I mean, just recently, the world has been celebrating some absolutely massive milestones in the traditional spaceflight arena.
Oh, absolutely. Huge achievements.
Right, like we watched the Artemis II mission preparations, getting ready to send humans back around the moon.
Yeah.
And we saw Blue Origin making headlines by reusing the new Glenn booster down in Florida. We are watching these colossal, towering metal skyscrapers filled to the brim with volatile, highly explosive chemicals roaring into the sky on pillars of fire.
It is awe-inspiring.
It shakes the ground. It's an event. But at the exact same time, a quiet, almost totally invisible revolution is happening in a laboratory at Texas A&M University.
Texas A&M.
Right. Scientists there are literally levitating and steering microscopic devices using lasers.
Using just light.
Right. They call them metajets. And the underlying physics of these tiny metajets could ultimately render those massive chemical rockets completely obsolete for deep space exploration.
The contrast there is just brilliant. I mean, you have the deafening roar and the massive thermal exhaust of the new Glenn booster on one side.
Yeah, pure power.
And on the other, you have complete silence and the invisible push of a laser beam in a pristine clean room.
It's wild.
The work coming out of the J. Mike Walker 66 Department of Mechanical Engineering at Texas A&M is fundamentally redefining how we even think about motion, momentum, and travel in space.
So who is leading this?
So there's Dr. Shufeng Lan, he's an assistant professor there, and the director of the Lab for Advanced Nanophotonics. He recently published a groundbreaking study with his team in the journal Newton.
The journal Newton, okay.
Right, and the paper is titled Optical Propulsion and Levitation of Metajets, and it outlines exactly how they are achieving this controlled three-dimensional motion using only laser light.
Okay, before we get into the microscopic engineering of an actual metajet, I think we really need to establish why this research is so absolutely necessary.
Why we need it at all.
Right. Like, why are we looking to completely abandon the chemical rocket technology that, took us to the moon and is taking us to Mars?
It's a fair question.
If you're listening to this on your commute right now, think about the engine in your car. It runs because you carry a heavy tank of gas with you. As you drive, you burn the gas, and your car gets slightly lighter. But rockets take that concept to a pretty punishing extreme, don't they?
They really do, and it is honestly a trap. Traditional rocketry is bound by this mathematical paradox known as the Tsiolkovsky rocket equation.
The Tsiolkovsky rocket equation.
Yes. In aerospace circles, they often just refer to it as the tyranny of the rocket equation.
The tyranny. That sounds dramatic.
Well, it dictates a very harsh reality. It says that if you want to move a payload through space, you need fuel. But fuel has mass. It is heavy.
Right.
So to push your payload and your heavy fuel, you need even more fuel.
Oh, I see where this is going.
And then you need more fuel to push that extra fuel.
It's like trying to plan a cross-country road trip where there are absolutely no gas stations. So you have to bring all the gas for the whole trip in your trunk.
That's a great way to think about it.
But the weight of all that gas means your car gets terrible mileage. So you have to tow a trailer full of more gas, which lowers your mileage even further.
Exactly.
You end up in this incredibly punishing cycle. You build a massive vehicle where 99% of the weight is just the explosive liquid required to get the remaining 1%, like the actual payload or the astronauts, to where they need to go.
That is a perfect way to visualize it. And that equation, as brutal as it is, works fine for our local neighborhood.
Right, going to the moon or whatever.
Yeah, we can use it to get to Earth orbit. We can use it to get to the moon. We can even use it to send rovers to Mars, provided we are patient and willing to wait months for them to arrive.
Sure.
But the moment you want to go incredibly fast, say a significant fraction of the speed of light, which is roughly 186,000 miles per second, the math completely breaks down.
Because the fuel gets too heavy.
Exactly. To reach Alpha Centauri in 20 years, you need to travel at about 20% the speed of light. The amount of chemical fuel you would need to accelerate a traditional spacecraft to that speed is physically impossible.
Like impossible.
Yeah, impossible. There isn't enough chemical energy in the known universe to make that equation balance out. The ship would be too massive to ever even move.
Wow. Okay, so light-powered propulsion completely sidesteps this tyranny.
It completely ignores it, yes.
Why doing what? Just leaving the gas station behind?
In a manner of speaking, yes. By leaving the power source behind.
Okay, unpack that for me.
Well, if your engine is a massive laser array sitting on Earth, or maybe sitting in orbit around the Earth, your spacecraft doesn't have to carry a single drop of fuel to power its journey.
Oh, I see.
It doesn't carry the engine, and it doesn't carry the propellant. It is just a payload and a sail riding the beam.
I just love the elegance of leaving the heavy machinery at home. It totally solves the math problem.
It really does.
But I have to admit, I struggle with the actual physical mechanics of this.
That's fair. It's very counterintuitive.
Because if I shine a really bright, high-powered flashlight at a piece of paper sitting on my desk, the paper doesn't move.
No, it doesn't.
It might get warm if the flashlight is bright enough, but it doesn't slide across the wood. How on earth does light, which is just photons, right? And photons have zero rest mass.
Correct.
How does something with no mass actually push a physical object?
It is highly counterintuitive because we don't experience the physical force of light in our daily macroscopic lives.
Right. We don't feel it.
We feel the heat of the sun, absolutely, but we don't feel it pushing us down into the sidewalk. But to understand this, we have to look at the dual nature of light.
The wave-particle duality.
Exactly. Light is both a wave and a particle. The particles, photons, don't have mass in the traditional sense of a rock or a bowling ball. But according to the laws of quantum mechanics and relativity, they do possess momentum.
Wait. If momentum is mass times velocity, and a photon has zero mass, how does it have momentum?
That is the exact question physicists wrestled with over a century ago.
Okay, good. So it's not just me.
No, not at all. The answer comes from James Clerk Maxwell and later Albert Einstein. While a photon has no rest mass, It has energy.
Okay.
And Einstein's extended equations show that energy and momentum are intrinsically linked. So even without mass, a photon carries a tiny, discrete packet of momentum.
A packet of momentum.
Yeah. Dr. Land uses a very helpful, tangible analogy in the research to explain how this momentum actually transfers to an object. Imagine you were throwing ping pong balls at a surface.
Okay, I am picturing throwing a bucket of ping pong balls at, like, a wooden board hanging from a string.
Right, exactly. Now, even though a ping pong ball is very light, when it strikes the board and bounces off, it transfers a tiny bit of its forward momentum to the board before it rebounds.
Oh, I see.
It physically pushes the board, making it swing slightly. Now, just scale that down. When a photon strikes an object and reflects off of it, it transfers its tiny packet of momentum to the object.
So the light from a laser is essentially a continuous, highly focused barrage of trillions upon trillions of microscopic ping pong balls bouncing off the surface of the spacecraft.
That is the exact mechanism. It is an incredibly tiny microscopic force, which is why your flashlight doesn't move the paper on your desk.
Right, because of friction.
Exactly.
Yeah.
The push of those photons from your flashlight is completely overwhelmed by the gravity of the Earth pulling the paper down, by the friction of the wood holding it in place, and even by the air pressure in the room pushing against it from all sides.
But if you remove that friction,
Yes.
if you place an object in the vacuum of space where there is absolutely no air resistance, no friction, and eventually no significant gravitational pull, that microscopic force becomes cumulative.
Cumulative, exactly.
Because in a vacuum, an object in motion stays in motion. So every single photon that bounces off adds a tiny fractional bit of speed.
A tiny push.
And because there is no drag, it never slows down. Over days, weeks, and years of continuous laser illumination, that continuous gentle push accelerates the object to unbelievable speeds.
Exactly. It's continuous acceleration. A chemical rocket burns all its fuel in a few minutes, giving the ship one massive shove, and then it coasts for the rest of the journey.
It's basically coasting on that one explosion.
Right. A laser-driven sail gets pushed constantly, second after second, year after year.
Okay, that definitely helps clarify the physics of the push. The vacuum of space allows that tiny cumulative force to just keep building.
Yes, it's all about the vacuum.
But that brings up an entirely new, incredibly complex problem in my mind.
Oh, I bet. What's that?
Well, understanding that light can push an object is one thing, but how do you keep it from just tumbling wildly out of control?
It's a stability issue.
Right, because to use another analogy, if I take a fire hose, which is shooting a very powerful stream of water, and I blast a piece of cardboard with it, the cardboard doesn't fly perfectly straight away from me.
No, it definitely wouldn't.
The water hits it, the cardboard tilts slightly, the water catches an edge, and suddenly the cardboard is flipping and spinning and getting blasted off to the side, completely out of the stream.
It just flies out of control.
Exactly. And a laser beam is narrow. If the spacecraft tilts even a fraction of a degree, won't it just slide right off the beam and get lost in the dark?
That is the million-dollar question.
So how are the scientists at Texas A&M actually controlling this motion?
That exact question is what makes this research so revolutionary. The stability problem you just described is one of the biggest hurdles in all of optical propulsion.
Okay.
The answer to how they solve it lies in the specific materials these metajets are made of. They aren't just using flat, shiny mirrors. They are composed of what are called metasurfaces.
Metasurfaces. Okay, we definitely need to break that down. What exactly are we looking at here? If I were holding a metajet in my hand, what would it look like?
Well, honestly, you wouldn't be able to see it in your hand.
Wait, really?
Really, to understand a metajet, you first have to understand the scale. We are talking about devices that are only tens of microns in size.
Tens of microns. Just to give the listener some real-world context for that, a single human red blood cell is about 8 microns across.
Right.
A single human hair is roughly 70 to 100 microns thick. So these entirely engineered functional devices are literally smaller than the width of a hair.
They are truly microscopic. They are manufactured in specialized clean rooms like the AggiFab nanofabrication facility at Texas A&M.
Okay, what goes on in there?
They use advanced lithography techniques. These are environments where even a single speck of dust is a massive boulder that could ruin the entire device.
Oh, wow, so it has to be perfectly clean.
Exactly. The researchers wear full protective bunny suits, working under special yellow lights to avoid exposing the photosensitive chemicals used in the manufacturing process.
That is intense. And what are they actually manufacturing at that tiny scale? Like, what makes it a metasurface and not just a tiny piece of foil?
So a metasurface is an ultra-thin material that has been engineered with incredibly tiny, complex geometric patterns on its surface.
Patterns.
Yes. Imagine a landscape of microscopic pillars, ridges, antennas, and valleys, all spaced apart at distances smaller than the wavelength of light itself.
Wait, smaller than the wavelength of light?
Yes, incredibly small. And these patterns are explicitly designed to interact with electromagnetic waves. In this case, the incoming laser light in highly specific ways.
So it's not just bouncing the light back like a dumb mirror. The physical shape of the material is doing something complex to the light.
Yes. When we talk about manipulating light, we usually talk about manipulating its phase, its amplitude, and its polarization.
Okay, let's pause and unpack those terms for those of us who aren't optical physicists.
Sure.
When you say the metasurface changes the phase of the light, what does that actually mean in practice? Are we talking about shifting the wave itself?
Yeah, so think of light as an ocean wave. It has peaks and valleys. The phase refers to where you are in that wave cycle. Are you at the crest or are you in the trough?
Okay, that makes sense.
By engineering these microscopic pillars of varying heights and widths on the metasurface, you can actually slow down certain parts of the incoming light wave just a tiny fraction of a second more than others.
Oh.
This shifts the peaks and valleys, altering the phase.
Okay, and amplitude and polarization.
So amplitude is essentially the intensity or the height of the wave, basically how bright it is.
Right.
And polarization refers to the orientation of the wave's oscillation. Is it waving up and down or left and right or maybe in a spiral?
Well, like polarized sunglasses blocking certain waves.
Exactly. A metasurface can change all of these properties simultaneously upon reflection. Think about how a traditional glass magnifying lens works.
Okay.
It relies on the physical curvature and the thickness of the glass to bend and focus the light passing through it.
Right, the glass itself bends it.
Right. A metasurface does the exact same thing. It shapes, bends, focuses, and steers the light. But it does it on a vastly smaller, thinner, and perfectly flat scale.
Without the curved glass.
Exactly. It uses those nanoscale geometric patterns to manipulate the light.
The level of nanoscale fabrication required to build something like that is just mind-bending.
It is an engineering marvel.
It's almost like building a macroscopic pinball machine or like a pachinko board where you carefully place all the bumpers and pegs so that when a ball, or in this case a photon, drops in, you know exactly which direction it's going to bounce out.
That is a highly accurate way to visualize it. You are engineering the microscopic bumpers to dictate the bounce.
I love that.
And here is the crucial distinction that really stood out about the Texas A&M approach. Historically, when people talked about moving things with lasers, the prevailing idea was that you had to perfectly shape and aim a highly complex adaptive laser beam to keep the object balanced.
Right, to stop it from sliding off like my cardboard example.
Okay. Exactly. The idea was if the object started to tilt, the laser beam on Earth would have to instantly detect that tilt and change its own shape to correct it. You had to do all the complicated work at the light source.
Which sounds like a nightmare if your spacecraft is a light year away.
It would be impossible.
Right, because the signal delay would be a year. If it tilts, you won't know for a year, and your correction won't reach it for another year. By then, the ship is just totally gone.
Exactly the problem. But Dr. Land's team flipped that entire paradigm on its head. Instead of trying to dynamically control the laser beam from afar, they built the control mechanism directly into the material itself.
Oh, wow. So the smarts are in the sail, not the wind.
Yes.
Yes.
Beautifully said. By carefully designing the shape, the orientation, and the placement of every single nanoscale feature on that metasurface, the scientists are dictating exactly how the light will bounce off, regardless of minor fluctuations in the beam.
So if the laser hits a specific pattern of microscopic pillars on the left side of the metajet, the light is purposely deflected at a specific angle, say down and to the left. Right. And because of Isaac Newton's third law, every action has an equal and opposite reaction, or the conservation of momentum. If the metasurface shoots the light down and left, the metajet itself gets pushed up and to the right.
That is the fundamental mechanism. The material basically acts as its own steering mechanism.
That is wild.
It tells the light how to push it. By altering the pattern across the surface, they can create restorative forces.
Restorative forces.
Yeah, so if the sail starts to drift to the edge of the beam, the engineered pattern on that edge interacts with the light in a way that automatically pushes it back into the center.
Oh, so it is totally self-stabilizing.
Exactly.
Well, if the material's doing all the steering automatically, what does that actually look like in practice? How much control do they really have over a device that is smaller than a red blood cell?
This leads us to the major first that Dr. Land's team achieved and published in the journal Newton. They demonstrated full three-dimensional maneuverability of these metajets using only a single laser source.
Three-dimensional. Okay, that is a massive leap. Because when I usually think of optical propulsion, I think of the concept of solar sails. We've seen these tested in space, like the Japanese Icaros mission.
Right, the Icaros mission.
And a solar sail is essentially a one-dimensional pusher. The sunlight hits the giant flat foil square, and the sail just gets blown forward, away from the sun. It's like a leaf blowing straight in the wind.
Yeah, simple 1D pushing is relatively straightforward. You just need a reflective surface.
Right.
But levitating an object with a laser and then intentionally steering it left, right, up, and down purely by controlling how the light interacts with the metasurface. That is a whole different level of complexity.
I can't even imagine.
To the team's knowledge, this is the very first time full 3D maneuvering has been demonstrated using this specific type of optical propulsion approach. They aren't just pushing the metajet, they are actively flying it.
Okay, I have to jump in here with a serious mechanical question.
Please do.
Because I'm really struggling with the 3D aspect, specifically the vertical movement.
The up and down.
Right. If the sail is just a flat surface, and a laser is hitting it from directly below, pushing up against gravity, I get how it goes up. You turn up the laser power, it rises.
Sure.
But how does it go down against the pressure of the laser? How do you pull something toward the light source using the light itself?
It is a phenomenal question, and it relies on incredibly subtle optical forces.
Okay.
When light interacts with these nanoscale structures, it doesn't just create a simple scattering force, which is the forward push we talked about with the ping pong balls.
Right.
It also creates what are called gradient forces.
Gradient forces. Okay, explain that.
Think of a laser beam. It is brightest in the very center, and the intensity fades as you move toward the edges of the beam.
Like a flashlight beam fading at the edges.
Exactly. That change in brightness is a gradient. When you engineer the metasurface correctly, the electromagnetic fields of the light interact with the material in a way that actually pulls the object toward the area of highest light intensity.
Wait, pulls it.
Yes. In certain configurations, the researchers can manipulate these gradient forces to counteract the scattering force, essentially creating an optical trap.
An optical trap.
Yeah, so by subtly tuning the polarization or the alignment of the laser, they can alter the balance between the forward push and the gradient pull, allowing the metajet to move downward closer to the source without actually turning the laser off.
That is staggering. They're using the internal structure of the light beam itself as a physical track to slide up and down on.
Exactly. It's brilliant.
But that brings me to my next bit of skepticism regarding how they actually prove this.
Skepticism is good. Let's hear it.
If these metajets are smaller than a human hair, and they are being manipulated by the incredibly delicate, invisible force of bouncing photons and gradient fields, wouldn't an experiment like that be completely impossible to run on Earth?
You'd think so, wouldn't you?
Right. Because I feel like even a slight draft from the HVAC system in the laboratory, or just the ambient gravity of the planet pulling down 100 times stronger than the light is pushing up, would instantly ruin the experiment.
Oh, for sure.
The metajet would just fall to the floor or get blown across the room.
Yeah.
How do you prove this works when you are stuck at the bottom of Earth's gravity well?
You are touching on one of the most difficult aspects of experimental design in this entire field.
Oh.
You are completely right. The force generated by the laser is microscopic, and Earth's gravity is relentless. If they just placed the metajet on a dry glass slide and shined a laser on it, it wouldn't levitate.
It would just sit there.
Exactly. Gravity and static friction would hold it down firmly. The researchers at Texas A&M had to come up with a very clever workaround to isolate these tiny optical forces. They conducted these experiments in a fluid environment.
A fluid environment. So they submerged the metajets in a liquid. What kind of liquid?
They typically use deionized water or specific optical oils.
Okay, why liquid?
By placing the metajets in a fluid, they utilize the physical principle of buoyancy. The upward buoyant force of the fluid, which is determined by the density of the liquid compared to the density of the metajet, helped to counterbalance the downward pull of gravity.
Oh.
It essentially created a pseudo-weightless environment.
Oh, that is a brilliant workaround. It's like astronauts training in the neutral buoyancy laboratory, that giant swimming pool down in Houston, to simulate spacewalks.
Yes.
The water makes them neutrally buoyant so they don't sink or float, allowing them to practice moving massive pieces of equipment using very little force.
It is the exact same concept, just scaled down to the microscopic level.
Yeah.
By neutralizing gravity with buoyancy, they created an environment where those incredibly delicate, light-induced forces were no longer overwhelmed.
So they could actually see what they were doing.
Exactly. They could shine the laser, watch the metajet respond to the momentum transfer and the gradient forces, and accurately observe and measure its three-dimensional motion under a microscope.
But wait, if they're operating in a fluid, doesn't that introduce a whole new set of problems?
It absolutely does.
Because water might make it buoyant. But to an object that is 10 microns wide, water isn't just water. At that microscopic scale, doesn't water behave more like thick syrup?
You are referring to life at a low Reynolds number.
Reynolds number.
Yeah, it's a fluid dynamics concept. Basically, yes, at the microscale, viscous forces absolutely dominate inertial forces.
Okay.
To a metajet, moving through water is like a human trying to swim through a pool of cold honey.
Oh, wow. That sounds awful.
It creates immense drag. And on top of that, you have Brownian motion.
Remind me what Brownian motion is.
It's the constant random bombardment of the metajet by the vibrating water molecules themselves, which creates this jittery random movement.
Oh, so the water is actively hitting it.
Constantly.
So they had to prove their laser steering worked despite the metajet being constantly battered by water molecules and fighting through microscopic molasses.
Which makes the fact that they achieved controlled 3D maneuverability even more impressive.
Yeah, I'll say.
The optical forces generated by the metasurface were strong enough and precise enough to overcome both the viscosity of the fluid and the chaos of Brownian motion.
Okay, the fluid bath proves the concept, and it proves that the metasurface design works.
Right.
The material is successfully steering the light to create precise 3D movement against heavy resistance. But a fluid bath in a Texas laboratory is definitely not the vacuum of interstellar space.
No, it is not.
If you're trying to prove a frictionless interstellar drive, testing it in microscopic molasses is a bit of a paradox, isn't it?
A bit, yes.
How are they planning to get these things into a true vacuum to see their actual top speed and behavior?
The fluid environment was an absolutely necessary stepping stone for the initial proof of concept, but as you pointed out, fluid brings drag. It creates friction that the metajet has to constantly fight against. To unleash the true efficiency and the staggering speed potential of light-driven propulsion, you really have to get out of the fluid and into a vacuum where there is no gravity, no buoyancy required, and no drag.
Out in space.
Exactly. Which brings us to the next massive hurdle for Dr. Land's team. They are currently pursuing external funding to take these metajets and test them in actual microgravity environments.
We are talking about getting these microscopic devices off the planet entirely.
Yes. The goal is to test them on platforms like the International Space Station, or perhaps utilizing parabolic flights.
Parabolic flights, those are the airplanes often called the vomit comet, right? The ones that fly in steep parabolic arcs.
Yes, exactly those.
They climb sharply and then dive, creating brief periods of weightlessness, about 20 to 30 seconds inside the cabin before they have to pull up again.
Correct. In those true microgravity environments, whether for 30 seconds on a plane or maybe months on the ISS, the pure physics of the optical propulsion can be isolated and studied without the interference of buoyancy or fluid dynamics.
That makes sense.
They can place the metajet in a vacuum chamber in microgravity, hit it with the laser, and finally see how it behaves when the only forces acting upon it are the photons.
And it is worth noting that Texas A&M isn't operating in a vacuum here. Pardon the pun.
Nice one.
There is a massive global race happening right now to crack the code on light-powered propulsion. This isn't just one lab's pet project.
Not at all.
The scientific community worldwide sees the writing on the wall regarding the limits of chemical rockets. We know that there are research groups all over Europe working on related optical concepts.
Oh, absolutely.
And here in the U.S., you have brilliant minds at the California Institute of Technology focusing heavily on propulsion stability.
Caltech's work is fascinating. They are deeply focused on that riding the beam problem we discussed earlier.
Oh, the slipping off the beam issue.
Right. If you are pushing a macroscopic spacecraft with a laser, it is inherently unstable. It's like trying to balance a bowling ball on the tip of a pencil or maybe a marble on a beach ball.
Right. The slightest deviation and it slides off.
Exactly. Caltech is working on theoretical nanoscale structures that inherently self-correct, much like what A&M is demonstrating practically.
You also have the Rochester Institute of Technology tackling the problem using diffractive grating platforms. What does that mean, diffractive gratings?
So a diffractive grating is an optical component with a periodic structure that splits and diffracts light into several beams traveling in different directions.
Wait, like, what? Give me a visual.
Think of the back of a CD or a DVD.
Oh, yeah, and how it reflects a rainbow of colors.
Yes, that's a simple diffraction grating. Rochester is exploring how those specific types of structures can be used to generate and control propulsive forces, somewhat parallel to the metasurface approach. It is a full-court press from the scientific community.
With all these heavy hitters, Caltech, Rochester, European space agencies, what makes Texas A&M's specific contribution so vital in this global race? What sets the Newton paper apart?
What makes Dr. Land's work so foundational is that they aren't just building a one-off device that happens to work through trial and error.
Right, they aren't just guessing.
No, they are advancing the entire field by developing a broader mathematical and physical framework. They are establishing the fundamental physics principles that universally describe exactly how light generates force across these engineered surfaces.
Oh, I see. So they are writing the foundational rulebook.
Exactly.
They are establishing the core math and the governing equations that everyone else, whether you're at Caltech or Rochester, can use to build and optimize their own devices.
Precisely. They are providing the underlying grammar for this new language of optical mechanics. And if those fundamental physics hold true as they move from the fluid bath into microgravity testing, it leads us to the ultimate question.
The Holy Grail.
The real holy grail of this research. How do we go from a microscopic, hair-width device levitating in a lab to a massive spacecraft capable of carrying actual human payloads or heavy scientific instruments to Alpha Centauri?
Here is where the data gets really interesting. And honestly, this is the part of the research that completely blew my mind.
Me too, honestly.
When you look at how traditional rocketry scales up, it's a nightmare of engineering.
Oh, it's terrible.
If you have a small rocket and you decide you want to carry twice as much cargo, you can't just make the rocket 10% bigger.
No, it doesn't work that way.
You have to completely redesign the engines to provide more thrust. To fuel those larger engines, you need exponentially more fuel.
Which means heavier tanks.
Right. And those heavier tanks require stronger, heavier structural materials to handle the immense stress of launch. It is a nonlinear compounding problem.
It's why the Saturn V was the size of a skyscraper just to send 3 men to the moon.
Exactly. But the most vital scaling principle discovered in this Texas A&M research is entirely different. The force generated by this optical propulsion depends on the power of the light, not the size of the device.
I want to pause and really emphasize how profound that realization is.
Please do.
The propulsive force depends on the optical power available, not the physical dimensions of the metajet.
Wow.
The underlying physics dictate that the exact same principles, the exact same equations, and the exact same nanoscale metasurface patterns that are currently pushing a 10-micron device in a fluid bath can push a massive interstellar spacecraft.
That is just, it's like we just invented a completely scalable engine.
It is entirely scalable.
If you build a microscopic metajet, you use a small laser pointer. If you want to move a larger ship, you don't need to fundamentally reinvent the physics of the metasurface. You just need to shine a more powerful laser at it. It is a completely linear path to scaling.
It separates the vehicle from the propulsion system completely. And when you extrapolate that out, you start to envision an infrastructure for the future of space exploration that looks completely different from what we have today.
We are talking about building massive, permanent infrastructure.
Yes.
Imagine enormous laser arrays, perhaps built on the dark side of the moon to avoid atmospheric distortion, or maybe orbiting the Earth, powered by square miles of solar panels harvesting raw energy from the sun.
It's incredible to picture.
These laser stations would act as the permanent engines for the entire solar system.
And the spacecraft themselves would be completely passive.
Right. No engines.
They wouldn't have massive fuel tanks. They wouldn't have complex combustion chambers or delicate exhaust nozzles that could melt or explode.
They're just empty shells.
Basically, they would essentially be engineered hulls covered in these highly specific nanoscale metasurfaces. You would have a fleet of fuelless ships traversing the solar system, ferrying cargo to Mars, and eventually venturing beyond the Oort cloud, all riding on beams of concentrated light.
It turns the spacecraft into a sailboat, and we control the wind.
A perfect analogy.
It fundamentally lowers the cost and complexity of the vehicle itself. You build the massive laser engine once, And you can use it to push 1,000 different ships over its lifetime.
Exactly.
But let me play devil's advocate here for a second.
Go for it.
Because space is not completely empty.
No, it's not.
There is the interstellar, medium tiny grains of dust, stray hydrogen atoms. If we are pushing a spacecraft to 20% the speed of light using these delicate nanoscale structures, what happens when it hits a speck of space dust at 37,000 miles per second?
That's a huge problem.
Won't that instantly obliterate the metasurface and leave the ship stranded?
That is one of the most critical engineering challenges for the actual implementation of an interstellar mission.
I would assume so.
At relativistic speeds, a grain of sand hits with the kinetic energy of a bomb. So yes, the metasurfaces will undoubtedly suffer degradation. Solutions currently being theorized involve heavily shielding the front of the craft and maybe putting the propulsive metasurfaces on the rear.
Oh, effectively pulling the craft rather than pushing it.
Exactly. Or, alternatively, creating highly redundant metasurface patterns where large portions can be destroyed without losing stability.
Like having thousands of extra sails.
Right. The material science will have to evolve to meet the harsh reality of the interstellar medium. But the key takeaway from Dr. Land's research is that the propulsive mechanism itself is viable.
The engine works. Now we just have to figure out how to build the chassis to survive the trip.
Precisely.
And that separation of power source from the vehicle really is the only realistic way we are currently aware of to achieve the speeds necessary to reach Alpha Centauri in a human lifetime.
It's our best bet.
A chemical rocket has a terminal velocity dictated by the chemical energy of its fuel. It can only push so hard. But a light sail, driven by a massive sustained laser array, can theoretically continue to accelerate up to a significant fraction of the speed of light, continuously adding velocity year after year.
It is basically breathtaking to think about the speeds attainable.
Yeah.
But, this research isn't just a hypothetical win for the astronauts and explorers of the distant future.
It's not.
No, the development of this technology is having a very tangible, immediate impact right now on the ground, specifically in how we educate the next generation of engineers.
Oh, that's a great point. We often forget the human element of these massive technological shifts.
Right, people actually have to build this.
A paradigm shift this large doesn't happen overnight, and it doesn't happen in a vacuum. It requires a tremendous amount of intellectual labor.
Absolutely.
And what's really inspiring about the work at the Lab for Advanced Nanophotonics is who is actually doing the heavy lifting. The design, the complex mathematical modeling, and the incredibly delicate experimental validation of these metajets were led by doctoral students in Dr. Land's group.
That is the beauty of the university research system.
Yeah.
The doctoral students are the ones in the clean rooms at the AggiFab nanofabrication facility, wearing the bunny suits, operating the electron beam lithography machines, actually manufacturing these nanoscale patterns.
They're doing the actual science.
They are the ones setting up the microscopes and running the fluid bath experiments, agonizing over the data when Brownian motion throws off their readings.
They are literally on the absolute frontier.
Yeah.
And the ripple effect of their work is already reshaping the curriculum at Texas A&M.
It really is.
Dr. Land noted that the underlying physics of these light-induced forces have already been incorporated into graduate coursework. They are literally writing the textbooks on optical mechanics as they discover it.
Which means we are witnessing a profound generational handover in engineering. Think about the aerospace engineers who trained in the 1950s and 60s.
The Apollo generation.
Exactly. They were masters of fluid dynamics, combustion, and thermodynamics. They learned how to control controlled explosions.
Right.
Now, the curriculum is having to shift to accommodate a completely new paradigm. The students today are learning quantum optics, nanomanufacturing, and electromagnetic momentum transfer.
It's a massive pivot.
Massive.
A technological leap of this magnitude cutting a 100,000-year journey down to 20 years is a multi-generational project.
Oh, for sure.
The doctoral students who are learning how to manipulate the momentum of photons today, and the undergraduates who are rushing to join these research opportunities because they read about metajets, they are the ones who will be the veteran senior engineers decades from now.
They will be the ones sitting in mission control, or maybe standing on the lunar surface monitoring the laser array, when the first actual interstellar probe powered by light leaves our solar system.
That gives me chills.
By integrating this cutting-edge research directly into the curriculum, the university is ensuring that the pipeline of talent is deeply fluent in this entirely new language of physics.
And it really ties into this broader scientific renaissance we are seeing across the materials science landscape.
We're seeing it everywhere.
The traditional boundaries of what we thought was possible are constantly being broken. We are seeing other researchers discovering hidden properties of light to power nanomachines in completely different contexts.
Right.
We are seeing teams using those same parabolic flights we talked about earlier to test things like graphene aerogels moving under laser power.
Graphene aerogels are another fantastic example of this paradigm shift.
What are those exactly?
They are incredibly porous, sponge-like structures made of carbon that are lighter than air. Because they have such low density but absorb and emit energy so efficiently, researchers are finding they can be pushed and manipulated by light in very similar ways to these metasurfaces.
Oh, interesting. So the university systems are having to adapt in real time just to keep up with how fast the physics are changing.
Exactly.
We are training a generation of students to view light not just as a way to illuminate a room or a way to transmit data through a fiber optic cable, but as a physical tool.
A literal wrench.
Right. A tool you can use to build, to levitate, and to propel objects.
It is a profound evolution in humanity's relationship with the electromagnetic spectrum. We are learning to harness the physical force of light itself.
It really is. So let's take a step back and look at the incredible journey we've just charted today.
We covered a lot of ground.
We really did. We started by looking at the harsh reality of the rocket equation and how it traps us in our local solar system.
The tyranny.
The tyranny.
Right.
Then we looked at a microscopic device, a metajet smaller than a single human red blood cell. We explored how scientists engineered its ultra-thin metasurface with nanoscale precision, building the 3D steering controls directly into the geometry of the material itself.
Putting the smarts in the sail.
Exactly. We saw how they successfully levitated and maneuvered it against the resistance of a fluid bath in a Texas laboratory, proving definitively that the tiny cumulative momentum of photons can be harnessed and directed.
And from that microscopic proof of concept, we traced the path forward.
Right.
We looked at the impending leap into microgravity testing, where the true efficiency of the design can be unleashed away from the friction of Earth.
On the ISS or the Vomit Comet.
Yeah. We discussed the monumental realization that this technology scales linearly based on the power of the light, not the size of the device, opening the door for massive macro-scale spacecraft powered by off-board laser arrays.
And finally, we saw how this exact research is actively cultivating the next generation of scientific minds who will turn this theory into reality.
It's super exciting.
Which brings us all the way back to our nearest stellar neighbor, Alpha Centauri.
Back to the night sky.
Right. We started this conversation talking about a 100,000-year journey in a massive explosion-powered rocket, a journey that would require generations to complete.
A civilization in a can.
Exactly. But if this technology fulfills its promise, if our primary method of moving through the cosmos transitions from carrying heavy, volatile chemical fuel to simply riding continuous, silent beams of light, it fundamentally changes humanity's relationship with space.
It changes everything.
It takes the vast, empty darkness that separates the stars and turns it into a navigable ocean of light.
It changes the very definition of distance in astrophysics. The universe basically becomes smaller.
It really does.
Yeah.
So I want to leave you with a profound thought to mull over as you go about your day.
Let's hear it.
If distance in space is no longer measured by how much fuel you could physically carry on a ship, but is instead limited simply by how bright of a light you can shine from Earth, what other seemingly impossible boundaries are about to disappear?